Okay, good morning, Professor David J. DelosReyes. Okay, my topic for this session will be college algebra, and we are now on lesson number 50. So, for those of you who are following my channel on college algebra, we are now on lesson number 50. Okay, let's proceed. The subject matter for this session will be college algebra, lesson number 50. The title of the topic will be How to Graph Logarithmic Function. The last time around, we have graphed the graph of the so-called exponential function, that is e to the x, something like that. But for this morning, we will be taking the graph or plotting the graph of a logarithmic function. Let us see what will be the variation of a logarithmic function if we try to graph it. Okay, let's proceed. I will try to give you an example problem. I will try to read the problem, graph the function, and specify the asymptotes and the intercepts. We are given the logarithmic function y equal to the natural logarithm of quantity x plus 2. Y equal to the natural logarithm of x plus 2. I still remember that equation because in the practical exams under the study of analytic geometry when I was still studying in the Philippines, I was given the equation y equal to natural logarithm of x plus 3. Okay, and to pass that exam, you go to the board and you must have to plot that graph, okay, within 3 minutes. So actually, this example problem is similar to the problem I have encountered in the Philippines when I was having a practical exam under analytic geometry. Okay, that is one of my terror professors in the Philippines. Okay, let's proceed. The given equation is y equal to the natural logarithm of the quantity x plus 2. If we try to bring out the graph of this one, there should be a solution. The solution is where is the location of the so-called y-intercept and x-intercept, if there are any. Okay, so the first step to plot the graph of this one is to solve for the intercepts. So I place it here, intercepts. When x is equal to 0, back to the given logarithmic equation, y should be equal to, when x is 0, it will just become natural logarithm of 2. So the y-intercept is actually existing. There is a y-intercept because when x is 0, y is equal to the natural logarithm of 2, and natural logarithm of 2, it should be a real number, and we could bring that out using the calculator. So we'll just display 2 on the calculator. We press the natural logarithm value, and the natural logarithm of 2 is 0.693. So meaning to say when x is 0, y is 0.693. So the location of the y-intercept is at the location 0 and 0.693. And if we try to go to the graph now, this should be the Cartesian coordinate system. Right? Y-axis, x-axis. According to our computation, the y-intercept is at the location when x is 0, y is 0.693. So the graph passes through the y-axis at this location here. Okay, that's the y-intercept. Y-intercept because it passes through the y-axis at the location x equal to 0 and the value y is 0.693. It's a real value. We could bring it out. It's not undefined. Okay, next one. We reverse the operation now. The first one, when x equal to 0, we can solve for the y-intercept. We reverse the operation. When y is equal to 0, back to the given original equation. We place y to be 0, so this should be 0 equal to the natural logarithm of quantity x plus 2. So we are now given a, what you call this, a logarithmic equation, right? And to compute for x, we must have to remove the guard. The guard is the natural logarithm over here. We must have to eliminate this natural logarithm over here. And from the concept of solving a logarithmic to exponential, okay, to remove the natural logarithm, we will take the antilog of both sides, the natural antilogarithm of both sides. So we raise both sides of the equation by the base e, because the base of the natural logarithm is e, so it will be e raised to 0 should be equal to e raised to the natural logarithm of quantity x plus 2. And e to the 0 is actually 1. Any number raised to 0 power is 1. And for the right hand side, okay, the antilog of the natural logarithm of any given function is just the given function. So the right hand side will just be simply x plus 2. Okay? Because the enemy of the natural logarithm is the value e if we try to raise it. Right? So e raised to the natural logarithm of x plus 2, meaning we are taking the antilog of that natural logarithm function. It will just be simply the given function. So 1 will be equal to x plus 2. Solving for x will be equal to 1 minus 2 after the transposition and rearranging. So x will be equal to negative 1. So there is a value of x when y is 0. So meaning to say the given logarithmic equation, okay, also crosses the x-axis at the location should be at negative 1 and 0. And where is that in the graph? This is the y-axis, x-axis. As per our computation, this is the y-intercept. And again, from the second computation, the location of the x-intercept, where it crosses the x-axis, is at the location negative 1 and 0. This is negative 1. It is to the left of the origin, right? And the ordinate is 0. So the graph crosses the x-axis at this location here, right? So actually, we got a partial graph. For the value of x going to the right, okay, we'll handle that one later on. But we know that the graph will be from this point to this point, so we connect this one. What will be the nature of the graph to the right of the y-axis? We could do that. So to determine the nature, the variation of the value of y to the right of the y-axis, we must have to plot additional points. That is, for the equation y equal to the natural logarithm of the quantity x plus 2, we put x here and we put the value y here. Then we use the so-called point plotting. We start with 0. When x is equal to 0, right, to the given equation, y should be equal to the natural logarithm of 0 plus 2, or will just be simply natural logarithm of 2. The value of y at that instant will be 0.693. It is actually this one. Or what will be the next location? We move a little bit to the right. When x is equal to 1, right, y will be natural logarithm of 3, and natural logarithm of 3 is 1.09. So a little bit to the right, this will be the point, right, 1.09. When x is equal to 2, y will be the natural logarithm of 4. The natural logarithm of 4 is 1.38. So meaning to say, when x is equal to 2, this will be the value of y, 1.38. When x is equal to 3, y will be the natural logarithm of 3 plus 2, which is 5, and the natural logarithm of 1.5 is 1.6. This is 1.6. So if you try to notice it, as we increase the value of x from 0 going to the right, meaning going to infinity, it's going to the biggest value possible. What will be the possible value of x? Y. It will also approach infinity. Because as you try to notice it, this is 1.6, 1.8, 1.9. So if the value of x is infinity, the natural log of a very, very big number will still be a very big number. So the value of y will still be infinity. So the graph will be going up like this. It will go up. Okay? So the range is actually from 0 to infinity. Right? So we know that the graph from to the right of the y-axis, it goes up gradually. Right? Because it goes from 0.693, 1.09, 1.38, 1.6, 1.129, it goes up till it reaches positive infinity. So we know that the graph, if we try to connect this will be the graph. And the equation for that graph is actually y equal to the natural logarithm of x plus 2. How about the nature of the graph from negative 1 to the value x equal to negative 2? Because the equation, this vertical line here is x equal to negative 2 is actually a vertical asymptote. Vertical asymptote. This vertical asymptote, this curve here, will not approach this vertical asymptote except at x may be equal to negative infinity. So, okay, let's try to get the value. Again, using the same equation. We'll move the value of x from negative 1 going to x equal to negative 2. Right? Negative 2. When x is equal to negative 1, y should be natural logarithm minus 1 plus 2. Minus 1 plus 2 is plus 1. And the natural logarithm of 1 is actually 0. Right? It is this point. When x is equal to negative 1.9, negative 1.9 is almost negative 2, right? But it's not yet negative 2. So if we try to take the difference of minus 1.9 plus 2, it will be 0.1. It will be 0.1. Okay? And 0.1, if we try to take the natural logarithm of this, it should be value 2.3, but it should be negative. So when x is almost negative 2, okay, the value of y is 2.3, maybe here. Okay? Right? When x is 1.91, we move a little bit, but it's not yet negative 2. The value of x, y will be the natural logarithm of 0.09. So you place 0.09 here, take the natural logarithm, the magnitude increases, but since the sign is negative, it should be less than. The value is actually negative 2.4. Right? So it might be here maybe. Right? And when x is equal to, we move on a little nearer to negative 2. Negative 1.99. Negative 1.99 is not yet negative 2. Right? So actually this curve here is tangent to this vertical asymptote. Okay? If the value of x is equal to negative 1.99, y should be the natural logarithm of 0.01. 0.01 natural logarithm, the value is negative 4.6. It is negative 4.6. It's going downward, right? Negative 4.6. Supposing when x is equal to negative 2, what will happen? If you try to place x equal to negative 2, y should be equal to the natural logarithm of minus 2 plus 2 will be 0. And there is no such thing as natural logarithm of 0. This is undefined. So, meaning to say, the graph did not cross the vertical asymptote. Okay? So, the graph is something like this. This is the vertical asymptote. The graph is like that. Okay? The vertical asymptote is tangent to the curve, but didn't touch each other. So actually, this is a vertical asymptote, and the equation is x equal to negative 2. So from the requirement of the problem, the asymptote is x equal to negative 2. This is a vertical asymptote. The curve did not cross the vertical asymptote except maybe at x equal to negative infinity, y equal to negative infinity. So the range of y is actually from negative infinity to positive infinity. The least value of y is actually negative infinity. It goes down very, very small, right? And to the right, it goes up. So the range of the given logarithmic equation is from negative infinity to positive infinity. And the domain is actually for the x value. The value of x should be from negative 2, okay? Right? Negative 2 to the left. And the maximum value will be positive infinity. So the domain x is actually from negative 2 to positive infinity. Okay, that's it, guys. The graph is this. It is tangent to the vertical asymptote. Then it goes up like this. It crosses the x-axis at negative 1 and 0. It crosses the y-axis at 0 and 0.693. Then it goes up. Right? It goes up. Then it goes down. But it will not cross the vertical asymptote. Okay, that's the graph of the given equation. Y equal to the natural logarithm of quantity x plus 2. Oh, that's very important. Okay, so for those of you who are studying college algebra, this is for you guys. If you want to subscribe to my channel is at youtube.com/ProfDavidJDelosReyes. If you want to share it, please click share. Try to watch my long video format discussion. I will assure you, you will get something from it. Okay, good morning from Los Angeles. Professor David J. Delos Reyes.